Uh, 922. There you go. Okay, so just real briefly, let's talk correlation. You're not actually going to be doing any lines of best fit or that sort of thing on the calculator, but they do kind of offhandedly mention a little bit of correlation stuff here. So just wanted to go through this. It's kind of random, I know, but so if you've got some kind of scatter plot, okay, and it seems like the dots are all clustered together, so it appears to be pretty linear, okay, we would call that a strong correlation. And if it appears as though the slope of the line is positive, or it's increasing, then we would say it's a strong positive correlation. So this example that I have right here, this is a strong positive. So likewise, a strong negative would be, it's still all clustering around what appears to be a line, but it's decreasing. So strong negative. And then we've got weak positive and weak negative, and you can probably guess what those look like. If it's a weak correlation, then it's not real well clustered together, but you can kind of still tell, maybe something like that. You can tell, okay, it's going up-ish, but they're not real tight together, so that would be a weak positive. And then a weak negative, you can probably guess. Not real tight together, but appears to be heading down. So something maybe sort of like that then, okay? And then if the dots are completely random, if there's no way to identify if it's increasing, decreasing, or whatever, for those we just say no correlation at all. Okay, so you really have 5 different options. Is it strong or weak? Is it positive or negative? Or is it simply just no correlation at all? Doesn't appear to be anything linear whatsoever. Okay, so I wanted to get into quadratics because that's going to be the main focus of what we're doing in section 2.1, but we did have this little bit of linear stuff we needed to kind of get through here. So, quadratic functions. They come in 2 varieties. There are quadratic functions that are written in standard form and quadratic functions that are written in vertex form. Okay, so standard form we've already seen. And this is the one you're probably going to use the most. Okay, that one. That one you're going to probably use the most because it lends itself to the quadratic formula, okay, with the A, the B, and the C and all of that. It's written in a form that's a lot like the other ones, too. So we tend to want to use standard form. Now, the vertex form, if our goal is to try and graph the thing, vertex form can be a little bit more helpful. And that one looks like this. Okay, where the H and the K are the vertex, the coordinates of the vertex. So what is a vertex of a quadratic? Think about the graph of a parabola. Yeah. Exactly. It's that highest or lowest point on a parabola. Okay. So if we know the coordinates of a vertex, useful information if our goal is to try and graph the equation that we have. Okay? So we're going to look at that. So if we have like an equation in standard form, and let's say we want to draw a graph of it, we're going to want to take that standard form equation, convert it into vertex form, and then use that vertex form to help us put a graph together. Okay? And so there's some different information that we can use to help us do it. Okay? So let's say that we've got, for example, a quadratic that's in standard form. How about 3x squared plus 12x plus 11. So we're going to take this guy, going to convert it into vertex form, and then use the vertex form to identify where the vertex is, and then graph the thing. Okay? All right, so putting it into vertex form is going to include the process of completing the square, which you guys did in Algebra 2 as well, to solve quadratics. Okay, it's not the same exact process of completing the square that you did in that case, because like I said, it was a different goal. The goal you had there was to solve a quadratic, to find the zeros and that sort of thing. And that's not what we're doing here. So this process actually ends up a little bit easier. But what we're going to do is, remember, we're trying to get it to look like this. So the first step that we do is we factor a number out of the first two terms only. So we can take a 3 out. So it looks like that. Okay. Now, do you see how we're getting there? Okay. We know A, and we know K. Now, the trick here is going to be in figuring out H, because what we have in the middle is not exactly the way we want it to be yet. Notice how it needs to be an x minus h squared. And right now, we've got x squared plus 4x. Okay? There's nothing squared on there yet. So what we need to do is we need to take whatever's in that little parenthesis there, and we got to complete that square. Okay? So what makes this thing, we have to add something to it. What makes that thing a perfect square? Anybody remember that process? How we figure out what that number is we need to add on the end to make it a perfect square? You're close. It's half of this squared. Okay? So take that second number, 4, chop it half and square it. So 2 squared, 4. Okay. Now, hold on a second. Haven't I just changed my function, though? Not just the look of it, but literally changed the value of it, too? I just added a random 4 in the middle. You're not supposed to be able to do that, right? In algebra, I can manipulate things, but I have to do the same thing to both sides of an equation. I have to make sure things stay balanced and all of that. I can't just say, oh, I need to put a 4 in the middle. I'm going to put in a 4. What? You can't do that. So, to keep this thing in balance, I need to, at the end of it, also add something to offset what I put in there. Negative 12. Good. Okay, so catch why that is. It's not just the 4, right? There's this 3 out front. It's technically what I added to the entire equation by putting this little plus 4 in the parentheses. Is I actually added a 12 because it's 3 times 4 if I were to distribute that 3 back through there. So to offset this thing that I did here, I have to subtract a 12 or add a negative 12, however you want to look at it. So, yeah, that's got to go there. Okay, and so now I can simplify up a little bit. First of all, x squared plus 4x plus 4, what is that written as a perfect square? X plus 2 squared, right? So 3x plus 2 squared. And then I've got this plus 11 minus 12. So what's that? Minus 1. And voila, I have it in vertex form. So what's my vertex? So it's minus h and plus k. So what's the h? Negative 2. And what's the k? Negative 1. Mm-hmm. Yep, so the vertex of that parabola is at negative 2, negative 1. So, if I'm going to start piecing together a graph here, I know that my vertex needs to be at negative 2, negative 1. Okay, so hooray, I got 1 point. That doesn't really tell me the whole story, though. So what else do I know about this parabola given its original equation? Yeah? Yeah. Because in vertex form, it is always x minus the h. Right now I have x plus 2, so technically that h would be a negative 2. You've got to switch the sign on it. Okay, so some other information about parabolas that you guys have studied in the past. How do we know if the parabola opens up or down? What tells us that? Yeah. Mm-hmm. What about that leading coefficient? Right. Okay, so should this parabola open up or down then? Up, because our original leading coefficient was a positive 3, right? So you know it opens up. Okay, so I'm going to give it a little opening up there. I don't know quite how wide yet, but I know it's going to open up. And then one other piece of information that you can use to help you kind of see how wide or skinny this thing is the last number here in the original equation, that plus 11. What is that plus 11? It's a y-intercept. Just like the number added at the end of a line is the y-intercept. Same thing with any polynomial, including a quadratic. Just think about this. If you were to plug in 0 for x, right? That's doing a y-intercept. If x is 0, what's the y? Well, if I plug in a 0, these first two terms go away and I get 11. So up this y-axis, I should have an intercept at 11. Okay, now the way I drew my scale, that's going to be up there a ways, because right now the way I was just counting by ones. So basically what that tells me, though, is I know that, yeah, this is where my vertex is, it opens up, but this thing is going to be a pretty darn skinny parabola. So it probably looks something about like this. Okay, so we got a good sense of what the graph of that thing looks like. So if I give you an equation in standard form of a quadratic, one expectation is going to be that you can sketch a graph of it effectively, using a y-intercept and knowing which direction it opens up or down. Okay, so let's jot down some of that information we just talked about that helped us do that. Okay, so the opening up and down. So if A is greater than 0, or if it's positive, that means it opens up. If that leading coefficient A is less than 0, it opens down. And then we also used C to help us out. That's a y-intercept, which will help give you an idea of scale as far as how much